Welcome to this Masterclass Explainer, everyone. Today we're going to demystify the core mathematical theories that make flawless, modern digital communication possible. Whether you're an engineering student trying to master this chunk of your communication syllabus, or just a curious mind wondering how in the world your phone streams 4K video without a single hitch, our objective today is simple. We are going to understand the fundamental limits of data.
Okay, let's just quickly glance at our agenda. We're covering 1. The noisy channel problem, 2. Modeling the digital pipes, 3. Finding the speed limit, 4. The information capacity theorem, and finally, 5. The magic of channel coding. Let's jump right in.
Before we even look at the math, we really have to ask ourselves a highly practical question. How on earth does a fragile little stream of ones and zeros travel from a cell tower, rip through the air, bounce off buildings, fight through chaotic atmospheric interference, and arrive all the way at your phone without being completely scrambled?
Section 1. The noisy channel problem.
You know, the life of a digital communications engineer is basically a constant juggling act. You've got three main balls in the air: the power of your transmitted signal, the bandwidth of your channel, and your reliability, which we measure as the bit error rate. You are constantly trading one of these commodities to keep the others stable. Want higher reliability, but you don't have extra power? Well, you're going to have to sacrifice some bandwidth.
Now, there's a really fascinating contrast between our two main types of coding. You might already be familiar with source coding, right? That compresses data by stripping out the unnecessary bits. Channel coding, though, it's the exact opposite. We are intentionally armoring our data with extra redundant bits specifically to fight off that channel noise.
And the crucial point here is that different real-world applications have completely different survival requirements. Take a standard voice call, for example. It can easily tolerate one error in every 10,000 bits, mostly because your brain just seamlessly fills in those tiny audio blips. But high-speed computing? No way! That demands near perfection. We're talking one error in 10 million bits. So we have to engineer our channel codes to meet these incredibly precise targets.
Section 2. Modeling the digital pipes.
To solve these problems, our most foundational abstraction is the discrete memoryless channel. By assuming the channel lacks memory, which basically means the fate of the last bit doesn't affect the current one at all, we can map the exact probability of inputs to outputs using a probability transition matrix. Honestly, this is our engineering superpower right here. It lets us turn totally unpredictable physical environments into nice, predictable statistics.
The absolute simplest version of this is the binary symmetric channel. Just imagine sending bits where there's a crossover probability, which we call P, that a bit flips. If you transmit a crisp, beautiful digital image through a binary symmetric channel with a 10% error rate, it's going to arrive looking like chaotic television static, unless of course we intervene.
Section 3. Finding the speed limit. So this ultimate limit is known as channel capacity, denoted by the letter C. Think of it as the maximum average mutual information in any single use of the channel, optimized over all possible input probabilities. Measured in bits per channel use, it literally defines the hard mathematical boundary of what our pipe can handle.
And this brings us to a monumental breakthrough in engineering history: Shannon's second theorem, the noisy channel coding theorem. Back in 1948, Claude Shannon shockingly proved that as long as we keep our information rate strictly less than or equal to the channel's capacity, we can achieve an arbitrarily low probability of error. But the very second you try to push data faster than that capacity, reliable communication becomes mathematically impossible. Full stop.
Section 4. The information capacity theorem.
Okay, here it is. In a single, wildly elegant formula derived by Shannon, we can instantly see the fundamental trade-off of our universe. Channel capacity, in bits per second, equals the bandwidth, W, multiplied by the log base 2 of 1 plus the signal-to-noise ratio. I'm not exaggerating when I say this equation governs literally every piece of wireless tech you own.
Because of that formula, communication design is incredibly flexible. If you severely lack transmission power, say, I don't know, you're a tiny probe transmitting data from deep space, you can totally compensate by using a much wider bandwidth to hit your target bit error rate. Just keep in mind, to actually reach this theoretical limit, your transmitted signals must statistically mimic Gaussian noise.
So what happens when you have multiple parallel channels available at once, like in modern Wi-Fi or 5G networks? Well, we use the brilliant water pouring algorithm. To maximize our total capacity, we physically allocate more of our limited power to the quieter channels and absolutely zero power to the noisiest ones.
It is exactly like pouring water into a vessel with a really uneven, bumpy terrain. The water naturally pools the deepest in the lowest, quietest valleys.
Section 5. The magic of channel coding.
To make this all work, everything relies on this one concept, the code rate. It's simply the ratio of actual, useful information bits, K, to the total encoded bits transmitted, N. Because we are constantly adding that extra redundant armor against noise, the code rate is always going to be less than 1. It represents the true amount of useful information you're actually getting through per transmission.
Let's look at the absolute simplest form of error correction out there, the repetition code. To send a 0, you just send 000. If a sudden burst of noise flips that middle bit, the receiver sees 010. But using simple majority logic, it realizes, oh, they probably meant 0. See? We intentionally sacrificed our bandwidth to absolutely guarantee survival. Modern codes, things like Hamming, BCH, and LDPC, they do this exact same thing, just with much more elegant matrix-based mathematics. But as we optimize these codes, trying to push our systems closer and closer to total perfection, we hit a hard, fundamental wall, -1.59 decibels. This highly specific number is the Shannon limit. It represents the absolute minimum signal-to-noise ratio required for reliable communication, even as you stretch your bandwidth all the way out toward infinity. You just cannot cheat the universe past this point.
As we wrap up this masterclass, I love this quote from coding pioneer Richard Hamming. It really brings us back to reality. He reminds us that all this elegant math, the matrices, the capacities, the logarithms, ultimately serves to build the very real physical systems powering our world. We don't just do the math for fun, we use it to build better, more reliable digital pipes. Thank you so much for joining this explainer. You now understand the fundamental limits of how information flows through our universe, but I'll leave you to ponder this one final thought. As our wireless technologies edge closer and closer to Shannon's theoretical boundary, what happens next? What does the future hold when we simply run out of room in the digital pipes? Until next time, keep questioning and keep learning.